Welcome to Math, Music, and More. Today we're going to talk about the square root of 2 and how to prove that it's an irrational number. Why is that such an important topic? One, it's an irrational number, and everything irrational is, of course, fun. And secondly, it's a great way to embark on the journey of learning how to do proofs. And then finally, I think it's a great opportunity to introduce one of the methods of creating proofs, and that is proof by contradiction. So let's get to it. So this proof is actually something that means something quite a bit to me personally, because it was actually the first question that ever stumped me. I always loved math as a kid. I loved physics my senior year in high school, mechanics, electromagnetism, etc. But I'd never done a proof before. And when someone asked me, just go prove that the square root of 2 is irrational, I just was like blank stare. So this therefore has some personal significance to me as well, because it's actually what ended up creating the hook for me to become interested in theoretical math, because I love just creating proofs. Lots of other things too, but that's one thing. So let's get right to it. The square root of 2, how do we prove it's irrational? Well, as I alluded to a moment ago, one of the techniques that we use in creating proofs, but not always, is something called proof by contradiction. Proof by contradiction, as the name implies, is that you assume the opposite of what it is you're trying to prove, and then you try to go through some basic manipulations to see if a contradiction emerges. And if a contradiction emerges, then by construct, the very first thing that you assumed must be wrong, and therefore the proof is complete. So let's go ahead and do that. Let's go ahead and just assume that the square root of 2 is a rational number, and then let's see if we can arrive at a contradiction. So how do we do that? We start by saying if the square root of 2 is in fact rational, it must be equal to some ratio of two integers. We'll call them m and n. Square root of 2 must be equal to m divided by n. Now, one of the things that I'm going to point out right now is that m and n could both be odd, and one of them could be odd and the other one could be even. But what's impossible is for both of them to be even. And why do I say that? Because if they're both even, we just factor out a 2 on both sides, numerator and denominator. If they're still even, we factor out another 2. So in other words, I'm inferring that m over n is the simplest form of the fraction, and therefore they could both be odd, but there's no way they could both be even. And that's an important side note here in this proof. So let's go ahead and just start with some arithmetic manipulations. If we just square both sides, well, the square root of 2 obviously just then becomes 2. And on the right-hand side of the equation, we just get m squared over n squared. Good enough. But let's continue a little further. If we just multiply both sides by n squared, we get 2n squared equals m squared. And this is where it starts to get interesting, because if we pause here for a moment, by virtue of the fact that m squared equals 2 times n squared, then m squared must be even. And furthermore, if m squared is even, then in fact m must be even. And why do we know that? Because you can't take an odd number and square it and then get an even number. So m squared is even, and m is also even. The wrinkle in all of this, which I find quite fascinating, and which I'll show to you in a moment just by showing some examples, is that if m is even and you square it, you have to get something that I'll refer to as double even, meaning you can divide it by 2 at least twice. But let's go ahead and prove that. If we were to create a quick little table of m and m squared, and we just looked at some even numbers, 2, 4, 6, 8, right? Well, what's 2 squared? That would just be 4. 4 squared is 16, 6 squared is 36, 8 squared is 64. Notice, as I mentioned before, that 4 can be divided by 2 twice. 16 can be divided by 2 twice. In fact, more than that. So the point is it's at least twice. 36, again, twice. 64, at least twice. That's what I mean when I say they are double even. They're more than just an even number. They can be divided by 2 at least 2 times. Now let's go back to this equation up here, because if m squared is double even, that means that if we cancel out 1, 2, we're left with m squared. But since m squared is double even, that means that n squared has to be an element of the set of even numbers. But what did we say before? We said before that one of them has to be even and one of them has to be odd. Well, if n squared is an element of the even numbers, then n also has to be an element of the even numbers. Because again, you can't take an odd number and square it and get an even number. So note, we are therefore saying that m squared is double even, m is even, and n is even. But that's a fundamental contradiction because we said this was expressed in simplest form and hence both numbers could not be even. Therefore, square root of 2, in fact, is an irrational number, and we can write my favorite acronym in the world, QED. Thus, it has been proven. So, thank you so much, and